Okay, so there are several terms to describe simple harmonic motion. All right. So first of all, equilibrium position. Okay, equilibrium position is actually where the acceleration and force exerted on the body is zero. Yeah, like you see here, this is the equilibrium position. Yeah, the force is zero, acceleration is zero. Okay, because no extension. Yeah, when the object is at equilibrium, the spring has no extension. Betul tak? No extension. So I can actually just write, write like that. When at equilibrium position, that means the y is equal to zero. Y is equal to zero. So we know that Hooke's law, right? Hooke's law, F equal to the force in the spring is equal to negative kx. But in over here we write as ky lah, because our extension is y. Yeah, use symbol y. So if y is zero, that means the force is zero. The force is zero. So that's why you say over here the force is zero. Okay, and then he also say acceleration also zero, because we know that acceleration is following the force, right? Because we have the formula total F equal to ma, and our force is only the restoring force. So when I can say that when the restoring force is zero, so acceleration also zero. Okay, acceleration also zero. So anyway, we also can say we have the formula, acceleration equal to negative omega square y. So y is zero, acceleration also zero, isn't it? Okay, so you can write this way also. Yeah, when a equal to negative omega square y. So when y is zero, when y is zero, when y is zero, acceleration also zero. Okay, so at equilibrium position, there is no acceleration, no force. Okay, displacement is using the symbol y. Okay, it's the distance from equilibrium position. Yeah, so how far from the equilibrium? That's the displacement, nah? Yeah, and then amplitude is the maximum. The maximum displacement. Maximum displacement. That's the amplitude. Okay, unit meter. Period is the time taken for one complete cycle. That means one complete oscillation. Yeah, period, the time for one oscillation. Unit second. Frequency is the number of complete cycles in 1 second. That means in 1 second, how many oscillation? In 1 second, how many oscillation happen? That is frequency. And then between frequency and period, it is frequency is 1 over period. Now this is an important formula. Yeah. So frequency unit is hertz. Yeah, or per second. Good. And then we have angular frequency. What is angular frequency? It is omega. We learned about omega, right? Still remember where do we learn omega? Omega is called another term we call angular. Class?
Angular velocity.
Angular velocity. We also call it angular velocity. Symbol omega also, isn't it? Unit is radian per second. So why here called angular frequency? So this angular frequency is called unit omega, is a symbol omega. Okay, it's called angular frequency when you in SHM, in simple harmonic motion, or mechanical, or in the mechanical wave, in the wave. We call this omega as angular frequency. But when in the chapter circular motion or rotational motion, in circular motion or rotational motion, we use velocity instead of frequency. Okay, like this. So in SHM, it has different name. It's called SHM. It's called angular frequency. In circular motion chapter or rotational motion, it's called angular velocity. But they are the same thing. Yeah, they are still omega. Okay, it's called angular frequency because it depends on how many oscillation. Yeah, how many oscillation in 1 second. Yeah. So okay. Just a different name, but it's the same thing lah. And then we have the restoring force. Okay, you already learned about restoring force. It's a force tends to bring a system back to equilibrium. That's why it's always towards. That's why the direction is always towards equilibrium position, because you want to bring back the object back to equilibrium. That's why the direction is always towards equilibrium. Okay, towards equilibrium. And it is proportional to the displacement. Yeah, that means if you have higher displacement, higher force lah. Actually, we use symbol y. Yeah, we use symbol y. Yeah, so higher displacement, higher restoring force. That means higher or longer elongation, higher elongation, or higher compression. Okay, larger elongation or larger compression. Then let me. All right. Okay. So larger elongation or larger compression, we have a higher spring force in the spring or restoring force. Okay. Understand everything? Okay, so let's look at kinematics. Now we want to look at kinematics of simple harmonic motion. So, what is kinematics? Kinematics is related to motion lah. It's about motion. It's about motion. Talking about displacement, velocity, acceleration. Those are kinematics. Okay, motion. So we want to know the equation. We want to know the equation. We want to know their graphs, you know, because before that you already learned about equation in linear motion, like, you know, v equal to u plus at, s equal to ut plus half at square. Those are for linear motion. But what about simple harmonic motion? We want to know their equation also. Yeah, so that we can what can we do with the equation? We can calculate. We can calculate their displacement at certain time. We can calculate their velocity at certain time. We can calculate their acceleration at certain time. And then we can somehow plot out their graph to show how the velocity, the displacement, the acceleration changes over time. Understand? So we need to know the characteristic first. Yeah, how to get this? We need to know how to derive. We need to know how to derive these equations. Okay, so that it gets meaningful. Yeah. The equations is meaningful to us. Okay, now look at here. So kinematic equation of motion for an object in simple harmonic motion can be found from the relationship between. How do we discover the kinematic equations of motion for SHM? Where can we discover? How we discover it? We discover it through the relationship between simple harmonic motion with uniform circular motion and sinusoidal curve. So actually there's one simulation I want to show you. Yeah. So hold on a second. Yeah, hold on a second. So please let me have some time to check out the simulation first. Yeah. Okay, so here I want to show you there is a good simulation to relate between simple harmonic motion with circular motion. So I want you to pay attention to how is this, you know, this simple harmonic motion related to simple circular motion. So please listen to this person. Yeah.
Of a record player. I have placed a yellow marker cap on it so we can observe the circular motion of the cap. Does everybody see that the cap is moving in circular motion?
Yeah.
Okay, now let me add a side view of the turntable and yellow marker cap. Do you see how the cap appears to...
So do you see this is the side view? Side view, that means I view from over here. Yeah, I view from the side over here. Over at the left hand side. I will view from the side. And what I see is this lah. Okay, so do you see this is like similar to simple harmonic motion? Yeah, this thing is very similar to simple harmonic motion. Please take a look.
To move in simple harmonic motion.
Yeah. No.
Okay, so then I will add appears to move in side view of the turntable and yellow marker cap. Do you see how the cap appears to move in simple harmonic motion?
Yeah. No.
Okay, so then I will add a vertical mass spring system moving in simple harmonic motion. Now do you see how the cap appears to move in simple harmonic motion?
Still? Yeah. Sure. Yep.
In fact, we can also add a front view of the turntable and yellow marker cap. And we can also add a pendulum moving in simple harmonic motion. Do you now see how the cap, when viewed from the side, moves in simple harmonic motion, just like a mass spring system and a pendulum?
I saw it from the start. Yeah, there's a lot going on in this.
Okay, sure. So there is a lot going on. So I will simplify it by removing everything but the turntable and yellow marker cap. Now I will add a dot that is motion tracked to the top of the cap. And I will isolate the motion of the dot so it is only moving in the y direction. This dot is now moving just like the side view of the cap. In other words, this dot is moving in simple harmonic motion. And watch the path it creates if we look at where the dot is located as a function of time. Does anybody recognize the shape of that curve?
Oh, that is a sine curve. Actually, I think it's a cosine curve. Actually, it could be either one. Sine and cosine are just shifted along the horizontal axis relative to one another. Right, Mr. P?
Yes, this could be a sine or a cosine curve. It just depends on where it starts along the horizontal axis. So remember, simple harmonic motion and circular motion are related because circular motion, when viewed from the side, is simple harmonic motion. Thank you very much for learning with me today. I enjoyed learning with you.
Okay, so can you see where is this? You see this? This is a very good simulation, isn't it? Okay, so class, want to hear comments from you. What do you think about this simulation? Class? So do you see anything in this simulation? Yeah? Yeah. So what do you think about this simulation? Is it interesting or let you have some idea or you learn something from it? What do you think?
The pendulum moving and the cap was moving like at the same time.
Yeah. So you see the students there also very responsive, right? Can you hear the sound from the YouTube?
Yes, sir.
Yeah. Their students very responsive. So like that lah. Yeah. So you see that's how this is a very good simulation. It really shows you how do you get this two view? This is the side view. View from the side. You can see actually when this thing move in the circular motion, when we view from the side, kita tengok dari tepi, kita tengok dari tepi. What we discover is actually the side view is a simple harmonic motion. Yeah, from over here we view from the down. Yeah, we view from downwards. We also see a simple harmonic motion. I mean the side view. Yeah, this whole thing is from the top is a plane view. Yeah, if you view from the side, it's actually become a simple harmonic motion similar to the spring mass system and also the simple pendulum. So have a watch again. Yeah, just briefly.
Mass spring system and a pendulum.
I saw it from the start. Yeah, there's a lot going on in this.
Okay, sure. So
A lot going on in it, yeah? Yeah, so later I will explain one by one.
there is a lot going on. So I will simplify it by removing everything but the turntable and yellow marker cap. Now I will add a dot that is motion tracked to the top of the cap. And I will isolate the motion of the dot so it is only moving in the y direction. This dot is now moving just like the side view of the cap. In other words, this dot is moving in simple harmonic motion. And watch the path it creates if we look at where the dot is located as a function of time. Does anybody recognize the shape of that curve?
Oh, that is a sine curve. Actually, I think it's a cosine curve. Actually, it could be either one.
So do you see it actually, this motion become like a sine curve? This is a sine curve, yeah? So now this is what we're going to learn, how to generate this sine graph, yeah? For, as you can see, this is actually this is actually the y component. You see the black dot here is actually the y component of this circular motion. Yeah, if you look carefully, it's this black dot is like a simple harmonic motion. Yeah, it is. It is the y component of this circular motion. So now, excuse me, it's a y component. Yeah. So now let's look back to the nodes. Yeah. So we have seen enough of the nodes of the simulation. So that's why we use symbol y. We use symbol y to represent the to represent the displacement. Okay, so let me. Okay, so can you see that the kinematic equation can be found through the relationship between simple harmonic motion with uniform circular motion and sinusoidal curve. Now you can understand this statement, isn't it? It is actually simple harmonic motion actually comes from uniform circular motion, and also it can generate a sine graph. So look at this object. When it oscillates, where do I have this? Hold on a second. Yeah, see, can you see that this circular motion is just like the spring mass system? I want you to see. This is here you can see the amplitude, right? See here? I want you to look at here. So this is the amplitude, isn't it? And over here, this line, this actually is the radius, correct or not, class?
Yes.
Correct, sir.
So do you see the length of the radius is actually the radius is actually the amplitude? From here to here. This is the equilibrium position lah. Do you see that? The radius is actually amplitude? Amplitude of this spring mass system. Can you see that?
Yes, sir.
Radius is amplitude. So I can say that actually all these radius, no matter where is the object, all of these are amplitude. Do you agree? Because they are the same radius, right? The radius is constant, kan?
Yes, sir.
So object does SHM behave very similar to object that move in a circle. The radius of the circle is actually amplitude, symbolic of amplitude A. Okay, good. So keep it. So right now I want you look at this simulation also. This simulation already show you. See that? See that? Simple harmonic motion, circular motion, and the sinusoidal graph. Okay, so let's go back to these notes again. Okay, so look at here. Now we want to derive the equation of velocity, acceleration, and kinetic energy and potential energy. So okay, now let's talk about displacement equation. Yeah, displacement equation. That means what is the symbol we put for SHM displacement? Y. Yeah, we use symbol Y. You know why we use symbol Y? Why we don't use X? Why we don't use X? Why we don't use x? We use y. Because it is a y component. Yeah, it is actually the y component. That's the reason. Okay. We want to get the SHM displacement equation in terms of time. So our focus here, what is our focus here? Our focus here is to find displacement time. We want to find the SHM equation for displacement versus time. So that means, let's say I have I get a time of let's say time at 10 seconds. What is the displacement? So if I substitute the time into the equation, I can get the displacement maybe 25 centimeter. Let's say. So that's why we need an equation for displacement. Okay. So let's say, so next time, if we give you a certain time, we can calculate out the displacement. Okay. But first, how to find the displacement equation for simple harmonic motion? Yeah, displacement equation, displacement versus time equation. So look carefully. That's why we need to relate between the simple harmonic motion to circular motion and then to sinusoidal curve. Okay, 3 things we need to pay attention. 3 things. So look carefully. So our focus here is to find this displacement equation. We want to know this equation. Okay. So but how? Okay. So maximum displacement is amplitude. Yeah. So it is related to this circular motion. So as I said just now, this radius is actually amplitude because you know when object has reached this point. Yeah, let's say object has reached. Sorry, let me draw. If object has reached this point, this radius becomes the amplitude, isn't it? When object is over here, this distance is amplitude. Okay. Before that, I want you to look again. Yeah, I want you to look again. To compare. So when object is over here, that means the ball start from here. Correct or not, class? Correct or not? And then the point is over here. Correct or not? Class, give me some response.
Yes.
If object has reached the amplitude, that means the ball is already reaching here. Correct or not?
Yes, sir.
And then the graph has reached here. Correct or not? And then when it go back to this position, that means the ball is over here, and then graph is over here, and then when the block has reached down over here, okay, that means the thing has oscillate to here. Correct or not?
Yes.
And then the graph has reached here, and then going back to the original position, that means the point has reached here, and then the whole thing has gone to here. So can you see one oscillation? This one oscillation, this is one rotation, and this is one wavelength. This is like one wavelength. Yeah. So I can say like from here to here is actually one period. One period to complete one wavelength. Okay. Class, can you get it?
Yes,
Yes,
sir.
sir.
Okay, let me rub off everything again. So just want to show you. Now you have seen it. Okay, so now look at how to get this equation. Our focus is we want to get this y equation. Okay, so how? So you can see this y actually is the same as this y. The y component of this y. You see, this is a right angle triangle. This is actually a right angle triangle, 90 degree over here. So you can see the y here. We want to know the length from here to here. Yeah, from here to here. This is actually y. This is actually y. So this y actually is the same as this y component of this amplitude. So this is the amplitude. This is the angle theta. So how to get the y? Y component of amplitude? You know this amplitude has x component and y component. Let me draw it out. So this is the x component and this is the y component. Agree or not?
Agree.
Yes.
Or we can write it as like this lah. We can write it as this is this is ax, this is ay. But we just write as y lah. We just write as y. We don't want no need to put the a. Just put as y. So this displacement actually is the y component of amplitude. So how to get the y component of amplitude? Ax is a cos theta kan? A cos theta. Ay is?
A sin.
Yeah, a sin theta. That's why the ay, which is the y component, is a sin theta. You see? A sin theta. Can you see it?
Yes, sir.
A sin theta. And then we have learned that in a circular motion, omega equal to theta over t. Because this one actually is uniform circular motion. One thing is this is a uniform circular motion. Uniform circular motion. So we can say when uniform circular motion, no acceleration kan? Alpha is 0 kan? No acceleration kan? So and then we have talking about velocity, we have this v equal to u plus at, s equal to ut. We have this formula s equal to ut plus half at square. So if in circular motion we translate it to s is theta, u is omega t, omega naught, and then plus a is alpha. Alpha, yeah. So uniform circular motion has no acceleration kan? No acceleration. So is there any alpha? Alpha is 0. So we only have theta equal to omega t. Understand not?
Yes, sir.
Theta is equal to omega t. So that's why, theta equal to omega t over here. So we can so we know theta equal to omega t. So this theta can be changed to omega t. This theta can be changed to omega t. You see, what is the theta? Theta is the angular displacement. Angular displacement. So we can change the theta into omega t. So we have a function of time over here. See that? We need the time because, as I said just now, our objective is we want to find an equation of displacement against time. So next time, if we put a time over here, let's say time equal to 10 seconds, we can calculate out the displacement. How many cm? How far is it from the equilibrium position? So that's why this theta need to change to omega t because we want to get a function of time. We want to get a function of time versus t. We want to get a function of displacement versus time. So this is a y versus time equation. You understand, class?
Yes, sir.
So we put a time, let's say 10 seconds, we can calculate out the displacement. Okay, so you see the displacement, it is actually the y component, it's the y component of amplitude. It's a y component amplitude. That's why we use symbol y. Okay, it is actually the y component of amplitude. And then, you see, this is a sine graph. A lot of things going on here, isn't it? I agree with the student just now in the YouTube. Yeah, a lot of things going on. Yeah, really. Yeah. So it is actually a sine graph. If you get this graph, actually it's a sine graph. It is and the amplitude is what? What is amplitude? What is the amplitude of the graph? A. Mathematics. It's the mathematics you learn, isn't it? You learn about trigonometry, kan? This is actually a trigonometry graph. sine graph in your trigonometry you learn. So the front over here, this is actually the maximum displacement. So I can say a lot of things going on here. So maximum displacement is amplitude. Because this is the y maximum. Y maximum. Y maximum amplitude. Okay. So that's it. That's it. And then about the period over here, the period over here actually can get from the omega over here. Do you know that? Because the omega is 2 pi over period. So that means if we know the value of, let's say, from this graph, it gives us the value of period over here. It gives us a value of period over here. We can find the omega for this equation. Like you see this graph. This graph, what is the period? What is a period? What is a period for this graph? From here up to this point, isn't it? So this is the period kan? Betul tak?
Yes.
So let's put into the equation. So period is 2 pi. Period is 2 pi, so omega is 2 pi over 2 pi lah. Betul tak? 2 pi over 2 pi. So let's cancel off, cancel off. So this is actually equal to 1. Equal to 1. So that means, what is this equation? Okay, so this equation is y equal to a sine omega t. That's the equation of the graph. And then we know the omega is equal to 1. So we can write it as y equal to a sine t. Because the omega equal to 1. Omega equal to 1. So omega equal to 1. So a sine t. That's a graph. That's the equation for this graph lah. Okay, and some more, if the equation give you, let's say, let's say this period, this amplitude is, let's say, 1 meter, kan? 1 meter. 1 meter. So the equation, we can put the amplitude as 1. So this is a 1. So y equal to sine t lah, the graph, because a equal to 1. A equal to 1. So you see, if it give us the value of amplitude, give us the value of period, we can find out using this equation, we can generate the equation. Using this general formula of displacement time equation, we can generate out the real displacement time equation for the graph, for the whole simple harmonic motion. Okay, class, you understand?
Yes, sir.
Yeah, good. Now I want to talk about velocity graph. Yeah, velocity graph. So I think time's almost up. Okay, but maybe just a little bit. Yeah, just breeze through. So the important thing is actually come from the displacement graph. Yeah. The next one is talking about how to find the velocity equation. Just now we got the equation for displacement time. How about velocity time? Velocity time. So last time is SHM equation for displacement time. How about the velocity time? Yeah. So we want to find the SHM equation for velocity versus time. That means I give up. Let's say I give a time of 10 seconds. What is the velocity? Maybe you calculate velocity is 23 meter per second. Yeah. So we need one equation for that. So how to get the equation? Just now, displacement is related to amplitude, right? It's the y component amplitude, kan? Now, velocity is Vy is related to y component of tangential velocity. Remember the circular motion? We have the tangent velocity. We have the tangent velocity of this circular motion, isn't it? So this Vy actually is the y component of this tangent velocity. So this one, I leave it to yourself. I won't discuss this. Here already show you how to derive. Yeah, actually you can read by yourself. Notice the velocity is maximum equilibrium and getting weaker approaches the amplitude. actually here it means that velocity is maximum at equilibrium, but it becomes 0 at amplitude. Yeah, because amplitude is stopped for a while. Yeah, like you see over here, my simulation over here. Where did I show my you see my simulation here? Velocity maximum where? Where is the velocity is maximum? Look at my simulation here. The object is fastest at which position? Object fast paling laju di mana?
Equilibrium.
Equilibrium kan, paling laju kan, betul tak? Even you see the red bar is the kinetic energy. You see, the kinetic energy is maximum at equilibrium, betul tak? Tapi kinetic energy is 0 at amplitude. The red bar actually is the kinetic energy. The green bar is the elastic potential energy. Ini macam saling tukar. Elastic potential energy tukar dengan kinetic energy. Because energy is conserved. Dia hanya tukar antara blok dengan spring. Tenaga diberi oleh spring kepada blok dan blok bagi balik energy kepada spring. Macam itulah. So, okay. Velocity maximum at velocity maximum at equilibrium. Tapi 0 at amplitude. Velocity 0 at amplitude because the blocks stop. You see? The block stop. The block stop. Fast, stop. Fast, stop. Fast, stop. Can you see that?
Yes, sir.
So velocity 0 dekat mana? Velocity 0 dekat mana? Velocity 0 at where? At amplitude. Velocity maximum at equilibrium. That's good. Thanks that you discover something over here. So, okay, itu maksud inilah. Okay, dan tadi dah kata displacement dah ambil dari mana? Ambil amplitude. Kalau velocity ambil dari Vy itu ambil dari tangent velocity. You see, velocity is tangent to the circle. So ambil dari tangent velocity. Okay, so since the spring is moved up and down, we get the SHM is the y component of the velocity. It is the y component of tangent velocity. So maksudnya ini theta. Dia sebenarnya sama dengan theta di sini. Kenapa? Nanti you tanya diri sendiri, ya. You tanya diri sendiri. Kenapa ini theta? Ini pun theta. Itu soalan saya bagi kamu sendiri. So you tak tahu lagi, nanti tanya saya. Okay? Theta di sini sama dengan theta di sini. So dia adalah komponen y of the tangent velocity. Komponen y of tangent velocity. So kalau komponen y dia adalah adjacent kan? Betul tak? Dia adjacent. Dia adjacent. Kalau adjacent kita cos theta kan?
Yeah.
Dia V cos theta. So adalah V cos theta. Tepatlah formula apa? Lepas tu tadi kata apa? Theta ialah omega T. Betul tak? Theta ialah omega T. So ganti saja theta tadi dengan omega T. Tepat sudah di sini kan? Betul tak? Omega T. Dan lepas tu kita tahu V equal to R omega. Ini formula yang general kan? Kita pernah belajar kan V equal to R omega?
Nah.
Lepas tu R itu, radius itu ialah amplitude. Kan tadi sudah belajar radius ialah amplitude. Radius is amplitude. So we substitute radius with amplitude. Then we can the V over here we substitute with A omega. So we get this graph, this equation, A omega over here. Okay. So that's why we get a graph, a cosine graph. Let's say if we draw a graph. Okay, this is the last lah. So after this we dismiss. So this is the graph for V velocity. Yeah, Vy versus T. So we get a cosine graph. Like that. Yeah, a cosine graph. make one more turn. So this is period, this is 2 period lah, like this. Yeah. So what is the maximum velocity? So this is the Vmax. You know. So the Vmax, Vmax is a omega. The Vmax is a omega. You know, a omega. So this is actually a omega, and here is negative a omega. Yeah. A omega is Vmax. The V maximum is a omega. Just now we learned what? Displacement maximum is amplitude kan? Now we learn Vmax is a omega. Yeah, we learn what displacement maximum is amplitude. So Vmax is a omega. Later you will learn maximum acceleration is a omega square. A omega square. So that's all for today. So I will discuss about acceleration equation later on. So, but you yourself can read yourself first lah. Yeah, you can read yourself first how to get the acceleration equation. Okay. So basically, this is the thing only lah. Yeah. So later I will come to you again. Yeah. So see you next time. Bye.
Thank you, sir.
Okay.